Hello, hello. Mario is giving a talk about totally new tool called ESME. Go on, Mario. Thanks.
Thanks to you. So, hello everybody. My name is Mario, and here I'm going to explain what ESME is and what it's for. So, this is the index of the talk. First, I'm going to introduce ESME, what it means, and why do we need it. Then I'm going to go over the most important design features at the moment, and finally show the current state and what's next. So, first, ESME is an acronym. It means Electric Sail Mission Expeditor. This is Andres's idea, this name. It's very hard for me to find names for things. I really like this name, especially because in the industry, it looks like names are either Greek mythology stuff or very convoluted acronyms. And this is so simple. He had to twist the dictionary just a little bit to get the expeditor word, but that's awesome. And as far as I know, it means I am or being in Latvian. And in Spanish, it reminds me to the word esmeralda, emerald. So yeah, that's nice, nicer than usual. So what is it? It's a mission analysis software that is designed especially for ESAIL missions. If somebody here doesn't know what an ESAIL is, there's a artistic representation by me on the right. Basically, if you have a stream of charged particles, and in the middle of that, you get a long, thin metallic tether and you charge it up, then you can deflect the particles and get a tiny bit of free thrust, basically, and you can use it for propulsion or for accelerating the decay of a satellite. The thing is that if you want to plan for an e-sailing mission, the current tools in the market cannot fully explain what it does. So first, the thrust comes from the interaction with the wind. So you need to simulate the wind at some point. There's low and constant thrust, like in chemical propulsion or light sails, but it comes, so it's not exactly like those. It decays more slowly than light sails, for example. And the thrust depends on multiple things like the voltage of the tether, the orientation of the tether with the wind, not with the light, geometry of the solar system, the weather in the sun itself. So in order to make a proper mission design, we need a special tool. So that's what we're making from scratch. I'm writing it in the Rust programming language. Happy to talk about why later. So about the details. First, I'm gonna talk about the space rope simulator that ESME is basically. So we have the problem of modeling an e-sail. We need to model it physically in order to find how the shape changes under the solar wind, and also how much thrust you can extract from the sun, from the solar wind. Here on the right is how a tether looks like currently. This is a multi-tether, which is multiple tethers made of aluminum with this redundant shape that it's made so that if there's a micrometeoroid impact and it breaks at some point, it can keep working. So in order to simulate that, there's an abstraction to be made, which is to instead model a rope, like one tether, let's say, and then this multi-tether thing can be added with scaling the values. And then, so first step would be to model a rope and then adding some stiffness to the rope, because aluminum is not, has some stiffness to it. It is flexible but not limitless. And starting with modeling a rope, it's very good because there are many tutorials around how to simulate a rope and videos and books and stuff. there's nothing about simulating multi-tethers. So had to start somewhere. And a further abstraction in order to simulate a rope is I started simulating a series of discrete points that can suffer forces individually, but they are also constrained into a rope-like shape so that they don't fly into space. So this is how it works. It uses an integration technique called Verlet integration. It seems to work fine for these purposes. So on the left you have the cube, it's a CubeSat, that's easy. And then the points, imagine that those are the points that form the rope that simulates the tether. And the user defines two things for this. The number of iterations per time step that ESME can use, because this is an iterative process and it needs enough iterations to converge. And then you need to define the distance you want each of these points to be at all times. So what happens is at every simulation time step, first the forces and the inertia, if there's some inertia from the previous time step, is calculated. Let's say that there's some force going up and to the right here. So all the points would move in this direction. Then the constraints come in because these points are keeping the correct distance, but they are flying into space. You don't want that. You want the first point to be attached to the CubeSat. So what you do is first you go over each pair of elements. In this case, it would be the origin point and the first element. And if they are farther apart than they should, which they are, you move them towards each other. In this case, the origin doesn't move, a movable object, so the other moves more, but you move them towards each other until they are at the distance d. Then you take the next pair, in this case 1 and 2. They are farther apart than they should, so you move them towards each other. And now note that the first one is incorrect again. Then you take the second and the third. They are farther apart than they should. You move them towards each other, and you continue doing this for every pair of objects in order. And when you're finished, you do it again and again and again for n times. And believe it or not, after some time, it converges into a rope-like structure, keeping the distance that it should, and the forces have been applied. So this is how the space rope is simulated at the moment, and how we can obtain the forces on each individual point, and also see how the shape of the tether changes. So the second design feature of ESME would be using the wrong tool for the right job. So here's a bit of a personal story. Back in university, I collaborated in a meteor detection station. For those who don't know about this, there's some stuff floating around in the solar system. Those are meteoroids. They are potential meteors. When they burn in the atmosphere, you get a meteor like here in the picture. And then if it reaches the ground without burning up, then it becomes a meteorite. And one of the objectives of the station was to record and catch these bright meteors. And if they were bright enough, then they might have left a meteorite. And if we managed to very quickly plot the orbit and figure out where it landed, we could get there before the meteoroid hunters, which is a profession that exists and it's very lucrative apparently. And if we got there before them, then we could get the meteorite for science instead of them selling it somewhere. And for figuring out where the meteorites landed, we used a program called UFO Analyzer, and with the coordinates of the camera and the orientation, we could get a solution for the orbit and figure out where the meteorite was. And for that, we had to check the background stars, mark some of the most important ones, and let the program run and find a solution. And we had a very important video that we could not make UFO Analyzer to find the orientation the problem was something like this. We had a low quality webcam pointing up with a fisheye lens in a very light polluted environment in Madrid. So the images weren't that good, and the program wasn't able to distinguish in that particular night what it needed. So we looked for the help of a professor of ours, Jaime Zamorano, and we told him what he needed. And without saying anything, with a straight face, he took our image, he opened it up in Microsoft fucking Paint, he got a brush, and he started marking all the stars with circles. And when he was finished playing, he said, now it will work. And it did work. And I find that glorious, not only because of the genius of painting on top of it and of thinking outside the box, but also because he used paint on a serious scientific matter. And yeah, I guess that story really resonated with me, because years later I've been using, not paint, but I've been using tools that I shouldn't use for scientific purposes, and it's kind of working. Here are some examples of other places in which the wrong tool has been used. On the left, you can see an asteroid generated with the asteroid image generator I've been working on for the past 3 years or so. For the rendering, it uses Blender. Blender is a software for 3D design, and it's meant for art, not for science. It's meant for animators, 3D artists, visual effects, and etc., but not for science. And down here, something that you all know probably, which is Ulysses, which they are using a Unreal Engine, a game engine, in order to simulate the lunar surface and drive a rover around. And so these are perfectly fine uses of tools that weren't meant for this. And there's only one small or big caveat, which is that these tools might contain dirty tricks. The bottom line, I would say, is that you can use these tools however you want, only you have to live in a constant state of paranoia. And I will explain why. So the thing is that the developers of these tools may have constraints different than the ones we have in science. So they may have been using tricks in the background that you are not aware of, and that they might interfere in what you're doing. So, for example, this is a diagram of how ray tracing should work in Blender and similar programs. So you have a set of rays. You throw a ray from the camera or the eye towards the object. In reality, it's the opposite way, but it's easier to think of this way. And so you throw a ray, it hits something, part of the energy reflects, and it may hit something else and reflect again. If the ray hits something transparent or translucent, it may go through, and then in the next transition, a rays are emitted, another one is reflected, etc. But so these programs are photorealistic, or so they claim, but they are not interested in being real. They are interested in looking as real as they can while being comfortable to use and everything. So they may be doing some things, like, for example, if you are not careful with Blender, by default, you may find yourself in the situation that the rays stop being reflected after some time. 1 minute, I will close the door. Sorry. So yeah, by default, Blender and some programs like that, they just drop rays after some time, after some number of reflections. And you should be aware of that. You should be paranoid so that it may be happening, and then you should find it out. And then you should wonder, is that affecting my work? Do I need those rays? If you need them, then you have to be careful of either bringing them back up or just making something yourself. There's something similar happening both in Blender. It can be happening in Blender definitely happen in video games, which is camera culling, which is that objects that are outside of the camera view might get deleted in order to save memory, or objects that are behind other objects might get deleted, and even parts of the objects that are not seen might get deleted. If you are in some situations, it may not mean anything. If you don't see it, then why does it matter? But if you are doing something photorealistic, maybe you need the rays that are bouncing on the back or on objects that are near your field of view. So you should think, is my tool doing this? Do I want it? Can I deactivate it if needed? Yeah, extreme paranoia, as I've said. And this is especially true with game engines because game developers are very known for playing very nasty tricks in order to keep their games running at 60 frames per second in all consoles or computers. There are some funny stories around. For example, here's one from back, and there's a mission where you have to go on a train. I don't know, I haven't played it, but the thing is that they realized that they hadn't programmed train tracks or anything like that in the game, and it was too late to do it, or maybe it wouldn't work and it wouldn't work in time. So can you hear me all right? I'm getting low connection stuff.
Hey, so you're dropping off every now and then. There are like a few seconds at some point.
Let me. I hope this is better. So yeah, so these guys got to the point where they had to simulate trains, and they didn't have that system in place. But what they had was people, and they had programmed hats. So they made a train hat, and they put it on your character, and they made your character slide around. So you thought that you were in a train, and that was good enough. And you have to consider that these people is the people that are making video game engines. And so they are being made by these people for these people. And these kind of tricks are expected, and they could be around everywhere. And you should be very careful of what they did. And so after all this, you may wonder, why am I using a game engine for ESME? And the solution is that I found some things that were useful and that I'm extremely paranoid all the time. So I'm using the Bevy game engine in Rust. It's very new. And the reason I'm using it is because I learned Rust last summer and I started writing a small game for that. And I started finding parallels, things that I could use in my future work in ESME. So I found it really useful for lots of things. For example, for creating graphics, especially 3D graphics. But so ESME started as a 2D simulator. And at some point I decided to turn it into a 3D simulator. And the change was literally 20 minutes using a game engine. I didn't have to worry about coding anything graphical myself. And then there are also tools for UI, for getting user input from keyboard and mouse. Video games need to control a large number of entities doing different things, and I can take advantage of that with my eSail because I need to control a large number of points in my sails. There's also built-in parallel processing, so they use it for stable 60 frames per second. I can use it for a really big sail with very high resolution. And also there are so many people, motivated people doing games that I can ask them anything. I can bring their expertise to science without them even knowing. And what is this game engine not useful for? Anything related to physics at all. I wouldn't trust it. There are ways, of course, integrated of doing physics and making things bounce, even rope simulators, but you don't know what they're doing with that. So I don't want them anywhere near my physics. So as long as I do everything related to physics myself, and I use Very for the, let's say, for the output and the input, then everything will be fine. So third part I wanted to go through quickly is that I've discovered that object-oriented programming isn't cool anymore. So in case for people who doesn't know this, and object-oriented programming is a programming paradigm. It's what I learned, and many people learn first when learning Python, and it can make your life simpler. It's based around objects that can inherit from other objects, so you avoid you structure your code in that abstraction, and you avoid writing the same code over and over again. This basic example everywhere for video games or something is that, for example, you want some humans in your game, so you make a human class that has some attack and defense, and then let's say you want to have an archer and a swordsman. So instead of repeating the code for attack and defense, you create the archer as a child of the human class, and the archer uses everything that the human has plus a bow, and the swordsman would use everything that a human has plus a sword. So you don't have to duplicate code, everything's very clean, but it can get messy very fast. For example, the main problem is when you want to have a class that shares capabilities with both more than one. And for some reasons that I won't explain, you cannot inherit from two classes at the same time. So you will have to add yet another inheritance from the base class. And now the bow and the sword code is duplicated. And if you want to have it, to not have it duplicated, then you have to be careful and do some extra stuff. And the thing that was helping you is not helping you anymore. So using this game engine discovered me that people don't use this approach in video games and anymore. There's a better alternative, and I'm so glad that I found it before I wrote a lot of code. And this approach is called an ECS, Entity Component System. The idea is that instead of inheriting from classes, you create very modular small pieces of code that can be reused. Everything in your simulation or game or whatever is an entity. And then you write several components. Each of them has a certain capability. And on top of that, you write systems, and systems go over the entities, select the ones that have the relevant components and act on them and only on them. So if we go back to the other example, if you have components, you can have an attack, a defense, a bow, and a sword component. And then when you want to create an archer, you create an entity and attach these three components that you need. And for the swordsman, you add the three that you need. And for the ranger, you add them all. There's no repeated code here. And then you can have a system running that, for example, it only checks the people with a bow. So we do the archer and the ranger, and it calculates the shot or whatever it is. So when I learned about this, I thought that it seemed very convenient for ESME. So here on the left, you have, again, the CubeSat and the sail. And at the end of the sail, you have an end mass, which is something that a heavy piece of metal that is not charged with the rest of the sail. And so there's a lot of shared code here, but some that is unique. So for example, for the CubeSat, I add a position, a rotation, and a mass component, and I don't need anything else. For the sail elements, I add the position, but I don't need the rotation. I add mass and include the voltage, and also a verlet element component, which means that the verlet simulation of the rope will check this. And then for the end mass, same as the sail element, but without the voltage. Now I can have systems that check only the required entities, and that gives, by accident, it makes your code able to be run in parallel. So you could have a thread that calculates the rotation of the CubeSat, and another thread at the same time can calculate the space rope. That can happen because the system that does the rotation doesn't need the sail elements and vice versa. So the code can run even faster. And the hope is that it can run in real time, and for now it's totally capable of doing that. And another design point of ESME is the discovery that your physics teacher was right all along. Let me explain. So imagine that you're back in school or high school or wherever, and you have to calculate the force, and you might have done something like this, right? You take mass and the acceleration, you multiply it, you even remember to add the trailing zero, you remember it's important, and everything is the International System of Units, so it's fine. And then your your physics teacher, who probably looked like this, he comes and says, 49 what? 49 what? 49 oranges, 49 apples. I cannot know. What is this? And you're like, it's a force. Do we really have to do this? But yeah, he always won, I guess, because he could give you grades. So this conflict was really active in the 90s, I guess, until 1998 when this happened. This is the Mars Climate Orbiter, and spacecraft from NASA. And the Mars part, they got to Mars, but the orbiter part, not so much, because it went much closer to the surface than they expected, and they lost contact with the ship. It probably burned into the atmosphere. And post-mortem analysis of what happened revealed that, so this is a NASA spacecraft, was in the United States, they don't like the International System of Units anymore a lot, but NASA does use it, so that shouldn't be a problem. But not all of their contractors use the International System of Units. I think it was Lockheed Martin who, for one of the last maneuvers near Mars, they provided an impulse in pounds force times second instead of newtons times second, and that made that resulted in a difference of almost 200 kilometers for the spacecraft, and it was lost. On that day, physics teachers of the world rejoiced, and they sang in unison, "I told you so, units are important. This wouldn't have happened if you were careful with it." And I finished physics many years ago. I don't want these guys to come to me and tell me I told you so. So I want to be very careful from now on. I don't want them to be able to do this to me. So I've been very careful with the units, but when you're programming anything related to physics, my experience is that doesn't work that well, because programming languages have lots of different types of variables, different types of numeric variables. You can have integers, you can have booleans, you can have floating point, but they are just numbers for the programming language. So you can write a force like this, for example, and that's it. It's just a number. Maybe you remember and you do proper code and you add comments. You add what the unit should be, or even better, you add the unit name to the variable name, and that way you can remember. But that doesn't work. He's not happy, and actually I'm not happy either, because one of the things that makes Rust special is that it prevents you from committing mistakes. If you made something unsafe in the code, it will not compile. Instead of it running and then failing what it's running, most of the times it fails during compilation. So you take more time when writing, but you're pretty certain that when it runs, it runs. But if you're working with units, then you can do something like this. You can write a force in newtons, and then there's another force written in kilonewtons. For some reason, maybe it's an input from the user or something. You remember to put the comments correctly. And you even add some exclamation points so you kind of forget, right? And then at some point, somewhere else in the code, you need the total force, and you just add them up, and everything's ruined because you get a 50 instead of 1049 in this case. And worse than that, it won't raise any alarms. So maybe it will take a lot of time to find out that something wrong is happening and where it's happening. Yeah, this shouldn't happen if I chose a programming language that it works for this. It prevents you from making mistakes. Why am I writing it in a way that is letting me make these big mistakes that could crash my spaceship into Mars? So I thought that probably somebody has thought about this. I looked around and yeah, definitely there's something called UOM, or units of measurement, which is a dimensional analysis package for Rust. And I've also found out that similar things exist for Python and C++ at least. So if I convince somebody to do this, but they use a different language, then maybe they can find a package that do the same thing. So when using this paradigm, this library, values stop being just variables and instead are instances of certain variable type. So for example, if I want to add a force to my program, I don't just write a variable, I write an object of the type force, and I specify the units, and then I specify the value. And if I want to add another force, I add it the same way, I specify the units and the value. And one very nice thing that it does is that internally it saves every variable as the base unit, in this case Newtons. So if I want to add a total force and I just add them up somewhere because I forgot they are different, nothing will happen because this addition will be made in Newtons. It will work. Also, the results of the operations like this addition are also dimensionally correct, so they have the units. The teacher is happy. And if you multiply a mass and an acceleration, you get a force automatically. It keeps track of that. And if you try to make something that is not allowed, like you cannot add kilograms and seconds, for example, if you by mistake do that, then it will not compile. So you will know what happened and where, instead of adding seconds and kilograms up and then figuring out why it's wrong 2 weeks later. So adding this to my program has been a lot of work, but I would say that it's totally worth it. A lot of work because, for example, you can make vectors out of variables, of course, of numbers. But if you want to make a vector of forces, that doesn't work that well anymore. So I had to make my own force vector, my own acceleration vector, and methods to change and operate between them. But as I said, I think it's totally worth it. I'm not coding for a spaceship, but if it was, it wouldn't crash anywhere, at least not for this reason. So here is the current state of ESME. You can see on the bottom, you can see the repository. As far as I know, nobody's using this other than me for now. So I'm very used to breaking things in production. If somebody starts using it and it gets angry because I keep breaking it, just tell me and I will move development to a different branch and keep a stable one there. So I have an interactive 3D environment that you can move with your mouse. The CubeSat and eSail and the endmass are simulated. The eSail can be deployed, not retracted for now, but that's not a priority. The Verlet integration of the sail is working, so the individual points of the space rope can feel the acceleration from the rotation and the Coulomb drag resulting in the solar wind and the voltage, and they move around as they should. And the solar wind thrust, the Coulomb drag, is compatible with Pekka Janhunen's paper of 2007. So yeah, the forces are there already. And some future work that is coming soon is adding the stiffness to the rope, adding real spacecraft rotation, because right now there is rotation, but it's a fake force going outwards. And the capability of adding multiple eSails, also retracting them at some point, and improving the thrust, the Coulomb drag calculation, because there's a more modern approach in another of Pekka Janhonen's papers, and I should upgrade to that one. Yeah, thanks for watching. That's everything for now. Open for questions.
Yeah, hello. This was amazing. I would even say we can upload it somewhere publicly. There was so much new stuff, new programming stuff that, yeah. What do you think, Mario?
Yeah, thank you. I'm glad you liked it. It's about uploading it somewhere. Yeah, I will be fine, or maybe retouching it or something. But yeah, I'm up for it.
All right, then I'll stop recording now.